Hello, we hope everyone is doing well. Welcome to our webinar series. Today we're going to cover generator selection based on load and temperature. My name is Mike Vermilye, Sales Area Manager located in Aiken, South Carolina. For our agenda today, we want to point out that we have Q&A available in the chat windows for the webinar. We have 2 sales engineers answering questions live. We'll also be doing email follow-ups to the questions as well, for those that require a little bit longer answer or maybe even some research. We are also going to look at the mechanical and electrical components of a generator set. We're going to review the power triangle. We're going to give you a power factor visual to help you understand power factor a little better, as well as reviewing the inductive and capacitive relationship. We're then going to look at the generator insulation class and the generator temperature class for its application. Also, we'll review the temperature over temperature curve. And in the end, we're going to be able to select a generator from the price list. So within the gen set, we have the mechanical component, which is the engine, rated in horsepower or kilowatt mechanical. To convert horsepower to kilowatt mechanical, simply multiply by 0.746. On the generator end, or alternator as some call it, this is rated in kVA or kW. The maximum kVA that you'll get out of a generator is the kilowatt mechanical multiplied by the efficiency factor of the generator. The efficiency factor of the generator can be located in the generator data sheet. If we want to convert kVA to kW, simply multiply the kVA by the power factor of the system. Power factor is also referred to as cosine phi or cosine theta. Let's look at the power triangle. Here we have A squared plus B squared is C squared. I'm sure we remember that 3, 4, 5 triangle, 3, 4, 5. Take those numbers and double them, that gives us 8 and 10. 8 relative to the kW, 10 the kVA. Since power factor is kW over kVA, this is simply 8 over 10, which represents an 80% power factor. Now, if we add some zeros to this, we have a 400 kW load, a 0.8 power factor, tells us we have a kVA load of 500. Again, this is based on a 0.8 power factor, which represents a 300 kVAR reactive load. Now, let's say a customer doesn't give you the kilowatts required or the kVA required, but they do provide the voltage and the current. It's very easy to calculate the required kVA. For a 3-phase system, we apply the square root of 3 times the voltage times the current divided by 1,000, and that gives us our kVA rating. So it really is that simple. Let's not make it more complex than we need to, going into trigonometric functions like sine, opposite over hypotenuse, cosine, tangent, etc. I also want to point out that if you're doing a single phase calculation, simply omit the square root of 3 from the formula. So here's a power factor visual that a lot of people can relate to. And the beer on the left here represents an 80% power factor, 0.8. So the working power is the liquid, the foam would be the reactive power or kVAR, and the total power is the kVA. Now, this would be typical where you have mixed loads, resistive loads, inductive loads, etc. In some cases, you'll have loads with a higher power factor. Perhaps the customer has corrected their power factor. And this next one represents a 0.9 or 90% power factor. Notice that there's more working power and less foam. All right, so this would be typical in a hydro application as well as many others. Where we have a high percentage or predominantly motor loads, we're going to see the power factor drop lower. A 0.7 is not uncommon. And we see a lot of this in the oil and gas industry. So if your power factor is less than 0.8, which is what we use as our average when sizing a 3-phase generator, we need to take that into consideration and derate the generator. Derating the generator will be covered in a future webinar. Next, let's take a little look at the inductance and capacitance relationship. I show this because this is often hard to visualize. When you use a simple clamp-on electric meter or amp meter or handheld meter, you're not seeing this relationship. But when we have inductive loads, the voltage leads the current. And this is an explanation as to why. But it pulls it out of phase. When we pull the voltage and the current out of phase, this refers to our power factors, that relationship there. So the area under the curve represents the power consumed. So as these get pulled further and further out of phase, we notice that the area below both of these curves gets larger, and that is the power being consumed. Now, when someone applies a power factor correction capacitor, the current leads the voltage, it pulls it the other way. So what the goal there is to pull those back into phase with the capacitors. So unity power factor is the goal for many, but usually you come close. Sometimes you only correct to a 0.9 because that's all the utility rate structure demands. For further questions on this, feel free to contact your local Marelli representative. Here we have the insulation class of the generator. Marelli uses class H for all of its low voltage units and class F as standard for all of its medium voltage units. So in the class H, we have a 40-degree ambient, as we do with all ratings, but we have a 125-degree permissible temperature rise. This means that the insulation of the generator can handle this degree of heat without breaking down. And so when you're comparing one generator to another, comparing bids, and you want to make sure you're comparing apples to apples, make sure that both units have the same insulation class. The insulation class determines how much material is going in, which also factors into the cost to manufacture the generator. Notice up here that we have a 15-degree buffer that we apply. So this gives us a little buffer if our ambient is higher than 40, but it's best not to use that in your sizing application. It's best to stick with the 125 range here as far as the design goes. But in our design, we do have a buffer. Next, we have the temperature rise class. So very, very similar to the insulation class. And what you find is you don't want your temperature rise class to exceed the insulation class of the generator. So it's perfectly fine to have an H-class insulation system and an F-class temperature rise application. But you certainly wouldn't want to reverse those because that would lead to a failed generator. And here again, we use the H for all the low voltage, F for the medium voltage. When we say low voltage, typically we're talking in the US up to the 480 volt range, and then medium voltage would be above that. Over temperature curve. So from time to time, you will go on temperature excursions, but you have to keep in mind that when you do this, you're taking life out of the generator. And the amount of life that you're taking out of the generator can be significant. So a simple 10-degree excess in temperature rise here can lead to a dramatic reduction in the life of the generator. So we definitely don't want to be exceeding the insulation class of that generator unless we absolutely have to, or in a dire emergency. So it's always best to give yourself some margin. Also, I mentioned this too because a lot of times we work with customers who are replacing failed units. And it's important to understand why the unit you failed or the unit you're replacing failed. And if it failed due to a thermal condition, then you're best off to maybe upsize the next generator to give yourself a little more operating margin. So here we are. We're now at the point where we can select a generator from our price list. So first of all, we have to ask ourselves, what voltage are we working with? Our price list is set up with the most common voltages that we work with on a day-to-day basis. And this would be 480 volt, three-phase, 240, 120, single phase, and 208, 120, three-phase Y. So the voltage, single phase or three-phase. Next, we have to look at standby or continuous. So we're allowed to run it a little hotter if we're only running it in a standby or a temporary application. If it's a continuous application, then we have to be a little more conservative with the temperatures to make sure we stay within the insulation class of the generator. I also want to point out here, I've circled it in red, that the power factor that we use for these calculations on a three-phase system is 0.8, as we see both locations here. The power factor that we use for a single-phase application is 1, predominantly because the single-phase applications are more for residential applications where you have a lot more resistive load versus inductive load. However, if you do know that your single-phase application has a lower power factor, we need to look at that. We need to review it. We need to look at derating the units. And again, derating will be covered in a future webinar. So once we've identified which area we want to work in here, then we're going to look at the temperature rise. So which of the temperature rises do we want to work with? So let's take a look at the MXB 160 MB4. That's the bottom row here, try to make it easy for us. This has the insulation class H, like I mentioned, a temperature max of 165 without that 15-degree buffer there, if you will, working in an ambient temperature of 40 degrees C. So if you've got a generator in a metal box sitting in the sun, that's something that maybe you need to take into consideration. And maybe we need to be looking at a different rating thermally for your unit to ensure that you're getting the life out of the generator that you would like to see. So a temperature rise H allows for 125 degrees C. Add that onto the 40-degree ambient, the total 165. So the maximum allowed power for this unit at that temperature rise is 17.5 kW. If we look at the temperature rise B, which allows for an 80 degree C rise over the 40-degree ambient for a total of 120, we would rate this at 14 kW, or it's rated at 14 kW. So again, we'll dive deeper into having to look at derating units based on the application. But in general terms, most people can come to this chart, follow the columns, select their generator, and you'll find that we usually have those generators in stock in our warehouse just outside of Atlanta. We want to thank you for attending today's webinar. Please remember, we'll be online for a few more minutes if you have some last-minute questions. And we also want to point out that our next webinar is going to cover data sheets and derating of the generators. Thank you very much.